Good morning. Welcome to this Conservation Applied Research and Development, or CARD, webinar today on optimized installations of air source heat pumps for single-family homes. Thanks so much for joining us. I'd like to cover a few housekeeping items before we get started. All attendees will be in listen-only mode. We will answer all questions at the end of the presentation, but as questions occur to you, please type them into the Q&A box and send them to all panelists. There may be some answers coming in through certain questions throughout the presentation as well. The Q&A box can be opened by clicking the ellipsis in the lower right of your screen as indicated on this slide. We will do our best to answer all questions within the time allocated, but if we don't get to some, we'll answer them after the webinar. This webinar is being recorded and will be available on the department's website. The slide set from this webinar is planned to be emailed out to all registrants within about 2 weeks from today. And finally, if you'd like closed captions on this webinar, click the CC bubble in the lower left of your screen. I am Lindsay Anderson, the Utility Energy Conservation Research Planner at the Minnesota Department of Commerce within the Division of Energy Resources. I work specifically within the Energy Conservation and Optimization Business Unit. In that role, I identify and analyze gaps within utility energy conservation and optimization programs and coordinate and plan research to fill those gaps. The CARD program is a major tool of that work. I also served as the department's project manager on the research that is the subject of this webinar today. Our presenters today are Ben Schoenbauer and Lindsay Genty from Center for Energy and Environment. Ben Schoenbauer is the Assistant Director of Research at CEE, where he researches new and innovative technologies and ideas dealing with residential and commercial energy efficiency. This work includes identifying new opportunities, conducting research, identifying funding opportunities to pursue, and disseminating the results. Ben's area of focus include water heater performance, service water heating, and residential HVAC systems. Ben has been with CE since 2008. He has his master's degree in mechanical engineering from the University of Minnesota and a bachelor's degree in physics from St. John's University. As a research analyst with CEE, Lindsay Genty also joins us today to present and provides data collection and analysis for CEE's various energy efficiency research projects in her role there. She is currently focusing on analyzing energy efficiency in retrofit homes and in HVAC systems. Lindsay is a graduate of the University of Arkansas, where she obtained her bachelor's in physics with a minor in mathematics. While in school, she helped gain local support to pass legislation on the Solar Access Act of 2019. Welcome, Ben and Lindsay. We look forward to your presentation today. This webinar is one in an ongoing series designed to summarize the results from research projects funded by Minnesota's Applied Research and Development Fund, which was established in the Next Generation Energy Act of 2007. The purpose of the fund is to help Minnesota utilities achieve their energy savings goal. $2.6 million is set aside annually for the CARD program, which awards research grants in a competitive request for proposal process. Results from CARD projects provide utilities with data to enhance energy efficiency program designs within their energy conservation and optimization portfolios. As you can see by the pie chart, CARD projects funded to date have been in all building sectors, as well as some that cross multiple sectors. The subject of today's webinar is within the residential sector, and we'll discuss results from a recent CARD project that installed and evaluated a sample of cold climate air source heat pumps in Minnesota homes to research the trade-offs of different air source heat pump applications and approaches, installation best practices, and the importance and impact of good controls and interactions with existing and supplemental heating sources to enhance utility eco programs and department regulatory processes. So with that, I look forward to, or I'm happy to hand it over to Ben and Lindsay, and I look forward to the presentation this afternoon.
Thanks, Lindsay. Yeah, we look forward to sharing our research results with everyone today as well. So on the screen now, you can see a brief agenda for the webinar today. We'll start with some quick background on CE, and a little bit of our history with work in air source heat pump technologies. We'll spend a few minutes talking about kind of what we've done in the past and where we are and why this project was important. Then we'll talk a little bit about the approach and methodology we used for this project specifically, cover results and lesson learned from our sites that we conducted research on in this project, and then wrap up with some kind of conclusions and recommendations and have time at the end for some questions. So starting with a little bit of background on CE for those unfamiliar. We're a nonprofit located in Minnesota. We focus on energy efficiency and energy solutions in kind of residential, commercial, and industrial buildings. We work in a lot of sectors in energy efficiency, and we really try to ground our work in real-world practical experience and focus on sort of community deployment, collaboration, scientific expertise, and equality and integrity in our work. This slide just kind of shows some of the areas that are at the core of CE's work. Like I said, we're pretty wide scoped in all kind of energy and efficiency applications in Minnesota, and really strive to use kind of on the ground research work like that gained through the CARD program to deliver good programs and opportunities across all these sectors. I know for people that are familiar, you've probably experienced CE in a lot of these different areas. And we're doing lots of work there, especially around heat pump technology. So a little bit of background on CE's work with heat pumps and why kind of this work is continued in this research project today. So we first started to look at field evaluations of this technology with a CARD-funded project that was actually funded back in 2014. That work was completed in 2017, and data collected in that project was some of the first available on cold climate installations of variable speed heat pump. This slide shows kind of 5 of the CARD-funded projects that CE completed in the past or is currently working on around air source heat pumps. We've also received funding from several other projects on heat pumps or heat pump related topics from a wide range of funders. So we really see heat pumps as a key technology for energy efficiency and decarbonization in the state and in the country. And we've made a big effort to help ensure that these installations in Minnesota really deliver on the promise of the technology. So you can see just from these project titles, kind of a range of focuses in single family and multifamily homes, really kind of starting initially with can these systems really work in Minnesota, and now moving into kind of a wider range of applications for this technology as it matures and we see more and more systems available. So really, what's the motivation for this specific research project? Well, like I mentioned, we started this original study back in 2014 through 2017, and we felt that study really demonstrated the potential of cold climate heat pumps in Minnesota, that the systems really have good performance and can lead to satisfied customers. But in that project, we required a lot of design work and installation and operational input sort of on the ground at each site, and working with contractors and homeowners to ensure that the systems were installed and operated in ways to ensure that they work well. So the plot on this screen shows some of that data from that project. If you've seen me talk about heat pumps, you've probably seen this plot before. Each kind of point on this plot represents a call for heat from a thermostat, and the orange points on here are really the heat pump only performance. And so you can see that at moderate temperatures, we are really delivering COPs or efficiencies up in that 3.55 range, and even down to temperatures as cold as 10 degrees outside, we're operating, twice as efficient as your standard forced air system. And so this project really showed the benefits of heat pumps and that they can really work in our climate. We focused early on ducted cold climate air source heat pumps to show this promise. Since then, the application types have really expanded and controls have changed. The landscapes around heat pump is growing dramatically. And so the focus as we continue on here is to look at kind of how these technology advancements and applications can be applied to limit some of that on the ground requirements to get best practices. And so that we can ensure that as heat pump installations ramp across sectors, that we really get the performance we want out of them, and that we hope to have. So as we move to optimized installations for single family heat pumps in this project, we are really focusing on cold climate heat pump designs, both centrally ducted systems where we're replacing existing air conditioners and furnaces or furnaces with whole house systems designed to meet the full load of the home through centrally ducted systems, as well as also including some ductless systems designed to integrate with those homes that don't have central ducting but have some other distributed heating sources. So we have a focus on both of those types of systems and what sorts of lessons we can learn about the best approaches to installation. So a little bit about the methodology. How do we approach this work? We started with doing some market interviews. We wanted to understand current best practices, where what contractors' approach to these installs was, how they were making choices, what utility programs existed, and if those programs were driving any of these decision making processes. Because this project was really funded before ECO was in effect, we really did we focused exclusively on electrically heated homes. Existing systems were all electrically heated. So we have some specific takeaways related to that, but also lessons learned here can really apply to heating systems of all fuel types. We designed some optimized installs, trying to kind of cost effectively replace existing electric resistance heat. We looked at the control of these systems to replace as much of that heat as possible. We really did some detailed monitoring performance all of those sites, and we kind of adjusted and optimized the systems over the course of the heating system as we could based on our findings. And then we went back at those kind of initial best installation practices and guides and tried to refine them based on the lessons we learned to come out with, at the end, some approaches that we feel are very important to consider as we move through kind of ramping up heat pump installations across all sectors. So jumping into kind of some of the actual work on the project, as I said, we started this project with a market assessment, looking at utility programs across the state, interviewing stakeholders to assess their awareness of heat pump technology and their plans for advancement in this area. The utility program has changed quite a bit over the landscape since we first started this project. Initially, a lot of the programs were pretty simple, mostly based around heat pump ratings, looking at installing systems with qualified HSPF and SEER efficiency ratings. As we've seen increased kind of policy and legislation around decarbonization and ramping up of heat pump interest, we're starting to see some of these programs change and modify, thinking about more advanced applications like cold climate or variable speed systems in particular, and putting requirements on different components of the installation above and beyond just HSPF and SEER. We expect to continue to see these programs grow as more and more federal funding is available, and other avenues for kind of specification like the NEEP cold climate heat pump spec and Energy Star advance their specifications as well. We also kind of interviewed stakeholders, focusing mainly on contractor interviews to try to understand general knowledge and interest in heat pumps, as well as gaps in to the market. I think the main takeaways from some of the contractor interviews were really around kind of this contractor preferences. Obviously, they're often tied to specific manufacturers based on their sales pathways and supply chain issues. And that does tie a lot of contractors into specific heat pump equipment choices. If a manufacturer they work with doesn't have a specific approach or application developed yet, then they might be more limited in those areas. We also saw a clear preference from contractors on sort of the more flexible installation systems. So ductless systems, multi-head systems, things that are simpler and more cost-effective for contractors to install. Had a clear preference from them. There also was an awareness of contractors of a lot of the design considerations we're going to talk about today, but some sort of implementation barriers that still exist. So, for example, they might be aware of the importance of sizing of a heat pump, but not trained or clear exactly on different implications of how different sizing choices might affect how a system runs. So we worked after the market assessment, we worked with those various channels, contractors and utilities, as well as some internal CE channels to recruit homes. Our goal here was really to create a large pool of potential sites so that we could select sites that really fit the project criteria. Those project criteria were to attempt to be representative of Minnesota's systems, both in the electrically heated market, but also more broadly. Because it's expensive to do the level of monitoring at these sites that we did, we knew we wouldn't have enough homes to sort of statistically represent the entire state. So we focused on sites that would cover the types of applications we expect to see, focusing on areas that we thought would be key moving forward based on sort of the market assessment. We also had to consider how easy it would be to instrument and collect data at these sites. While we don't expect that to expect performance, if there were some physical restrictions in the home or lack of access for our staff, we had to prioritize other sites where we could more easily monitor performance. So I wanted to take a few minutes here before we get into results from kind of specific sites to walk through kind of what our approach to installing these systems were from the beginning of the project. This sort of set the baseline for how these systems operated, and then we sort of tried to optimize and improve efficiencies and performance as we went along through the project, and then revisited these kind of approaches and goals at the end of the project to see, where we could improve them, what benefits were there, and which ones needed to be enhanced. And so this is kind of can be thought of as like our baseline of installation best practices at the beginning of the project. So starting off, the kind of key baseline thinking here is that the approach to each site does need to be tailored a bit to kind of the characterization of the occupants in the home that the install is happening in. Things to focus on here were kind of the occupants' goals and approach to the system. So how the system was going to be run once installed. And this included things like, prioritization of operating cost compared to emissions and decarbonization, replacement of existing systems versus displacement. Was the house trying to go fully electric, or did they just want to offset some fuel costs in a fuel switching application? Were they trying in an electric resistance install? Are they trying to eliminate some baseboard systems or just offset some of the heating use? Or do they not have a particular feeling about that type of thing at all? Then also we need to match the heat pump approach and application to the existing system. Making choices like ductless systems versus multi-head systems versus central systems. And then we have to consider how these systems are actually going to be controlled. So just an example of this shown in the plot at the right is a comparison of a cold climate air source heat pump to a single stage heat pump. This plot shows capacity of the systems versus outdoor air temperature. And the black line here shows like a typical home heating load. This is maybe a little bigger of a home for our range of systems, but a heating load nonetheless. So it takes 50,000 BTU per hour to heat this site at 0 degrees. And so the choice here is, you have a single stage that can deliver the capacity as shown in gold on this chart, which meets the heating load of the house down to about 30 degrees outside, which might be a good application if you're a cost-conscious person that only wants to offset, moderate heating loads with a heat pump. But if you are interested in pushing the system, getting all the heat pump operation you can out of it, really focusing on kind of emissions reduction, or you have a pretty inefficient existing system, you might want to push the heat pump operation down to colder and colder temperatures. And so, understanding that a cold climate variable speed heat pump is shown in kind of the green there at its max operating speed can match the heating load down to 20 in this case. So you have sort of a choice there between single stage and dual stage, and you should tailor that to what the needs are at the site. So kind of similar to the last discussion, the importance of relying on sizing and the importance of sizing on how the system will run in the home. This again kind of has this similar discussion about kind of what the goals of the system are versus the size of the heat pump that install the site. This plot on the right kind of shows a 2-ton system in red all the way up to the same brand name 5-ton system in purple. And you can see with that the 2-ton system, we're only meeting the heating load to a moderate temperature of the house, even when the heat pump's fully ramped up. But if you oversize too much and pick too big of a system, the minimum heating load of that kind of 5-ton system is always higher than the heating range load of this specific house. And so it's always going to be sort of turning on and off and short cycling to meet the load. And so knowing kind of the heating load of the house and what the application of the system is pretty important. I do also want to, this is especially important for ductless systems. It's kind of the approach you want to use or how much, heating you want to try to deliver with the heat pump. So this is a bid shown on the screen for about a 2,000 square foot home. I think it was actually 2,500 square foot home. And we just went to a contractor and asked for a heat pump bid just to see what they would come back with. And the approach used here was to put a ductless heat pump solution and put a head in every single room in the house. You can see that's 9 different heads in this particular install with a pretty hefty price tag to do those installs. It's $60,000 to replace your HVAC system. And so that's obviously a pretty expensive install. And you have to question, are you going to heat that pool table room enough to justify that cost of a specific indoor head just for that site? So things like that, understanding the cost effectiveness of expanding more and more heat delivered to the home. And the final piece I'll touch on our kind of guided controls approach is controls. This can be everything from a fully integrated control that requires you to rewire or run the operation of every piece of your heating system. So in a ductless install, this is every baseboard radiator that's a backup, or your gas furnace or gas fireplace, or sort of all heat pumps through one central system. Which comes with a lot more features and control options, but is a much higher cost. We also have on the cheaper end, sort of just relying on thermostats and the calls for heat to control various systems, which is obviously cheaper, but has less ability to directly control all components of the systems. We also have some third-party controls kind of in the middle there that sort of use Wi-Fi communications and some oftentimes sort of independent temperature sensors to try to do the best they can to prioritize different system operations. So we took all these lessons learned and we tried to install them on each of the test sites. We really did focus on 2 types of installs, sort of centralized systems as shown on the right of this screen, ducted systems that kind of delivered heating and cooling with the heat pump to all zones of the house. And then on the left-hand side, for anything that didn't have a centrally ducted system, we utilized ductless options, focusing, like I said, mostly on multi-head systems to really deliver benefits of multiple zones of heating from a single outdoor unit. So with that as a background, I'll pass the presentation over to Lindsay to discuss our monitoring approach and how we collected data.
Thanks, Ben. So I'm going to be talking a little bit today just about our field data that we collected during the project. So the main goal of this project was to capture real-world data to provide insight for the field performance, as well as to give recommendations on how to improve that performance of a heat pump. So as many of you probably know, a heat pump is a heat transfer system to determine the overall performance of that system. We calculate the COP, or the coefficient of performance. The COP is a ratio of energy input to energy output, and the energy input is the electrical consumption used by the system in order to operate. The energy output is the delivered energy to the space in the form of heating and cooling. In the image here, you can just see how a normal heat cycle would work for a heat pump. I won't get too much into detail with that, but the point is that during one of these cycles, we would have sensors placed at various stages in this cycle, and we would capture high resolution data to have a better understanding of these modes of operation. So I'll get into those inputs now. So collecting information about the energy input and output is essential to know the performance of the heat pump. To start simply, the energy input is a direct measurement we can take using a power meter known as an E-gauge that you see there on the right. The power meter directly monitors the consumption for each heating element that's within the house, used by CTs that are wired directly into a breaker panel. The energy output of a system isn't a direct measurement, but rather it's a calculation based on other measurements we have within the system. So we capture measurements such as the supply and return temperatures using thermocouple arrays that you see there on the left side of the screen, connected to a Campbell logger. Other collected measurements are things like the temperature of the outdoor coil or the amperage of the supply fan, and we use all of these different variables to analyze the modes of operation. I mentioned that we collected high resolution data. That's just to say that we collected 1 second data for the course of about a year for each of our sites. Some sites had as many as 3 years worth of data, and all the data that we collected was passed through quality control checks just to ensure that we had the most consistent and robust data for later analysis. So here's a summary of all the sites that we monitored during the project. A total of 7 sites were recruited, and our goal, as Ben was mentioning, is to have the most representative sample of existing heating systems across the state in a small sample set. So that middle column there, you can see what such existing systems looked like. We did find that most sites had really complex heating sources. Some of the homes had as many as 3 different types of sources to heat their home at once. We'll touch on this a little bit later, but such variation added complexities to what heat pump could be installed, how it would be installed, and most importantly, how would it be controlled. So in the last column there, you can see which heat pump approach we ended up using in the end. So for mini splits in particular, they can be a little bit complicated to integrate with existing systems, primarily because they don't use a central thermostat like some other systems do. So we tried to find opportunities where additional controls could be implemented that prioritized the heat pump usage over the other heating sources within the home. This not only would improve the heat pump performance, but also, depending on the situation, could also streamline the overall operation for the homeowner as well. So before we get too far in the weeds on site-by-site analysis, we wanted to make a few comments about the captured field data. So first, it's important to characterize the installed performance of a heat pump to understand the true performance. Field performance in general is not as good as the measured performance in a laboratory. That's because laboratory ratings are based on controlled conditions that are not directly comparable to ever-changing conditions you might see out in the field. Of course, that's not to say heat pumps perform poorly, because they still perform much better than your traditional HVAC systems, but normally we see lower COPs out in the field than manufacturer specifications. Some of the impacts and factors that impact the performance are difficulty to replicate in a lab, or things like occupant behavior. Trying to anticipate whether a homeowner might manually adjust their thermostat constantly, leave it alone, do a mixture of the two. Weather conditions can be variable from year to year. Other impacts are limitations of the sensors that we deploy in homes. So the accuracy and sensitivity of our sensors may also vary than what we measure in the lab. So these are just a few things to keep in mind as we proceed through the presentation. One example of a field measurement that is difficult to capture on site are our airflow testing. So CE, along with other national labs, research groups, and sensor manufacturers, such as the Energy Conservatory, have conducted a lot of testing and trials to try to understand and improve the accuracy of these airflow measurements. We are happy with the measurements that we do get. We do think they're fairly accurate and they're fairly consistent with the manufacturer specifications, though we usually get a slightly lower airflow than what is specified by the manufacturers. So we have two types of tools that we use to do airflow testing on the left-hand side and in the middle of the screen. These are TrueFlow plates that we purchased through the Energy Conservatory, and they're used for ducted systems. And then the image on the far right is how we would set up an airflow test for a mini split system. So the plates are pretty straightforward. You place a TrueFlow plate where an air filter would go in the ducted system, and you can directly measure the CFM or airflow of that system. The example on the right is slightly more complicated, but inside the box is the indoor head to the mini split system. And you're essentially creating a miniature ducted system with the box and tape that creates a seal around the mini split. The pressure that's created within the box is what we measure and use to determine the airflow of that. Both of these methods do have a bit of margin of error just due to some site conditions. Something that comes up quite a bit is tape not completely adhering to the wall, creating a perfect seal around the box, for example. So getting a good enough pressure to get higher airflow can be challenging. But despite these challenges with the field measurements, we are confident with the accuracy of data we do collect. And with that, I will pass it back to Ben.
All right, thanks, Lindsay. So with that said, let's move into some of the actual installs from our data and some of the things we picked up at each of the sites. As Lindsay mentioned, we collected 1 second data for up to 3 years at some of these sites. So we have tons of information that we can get. So we wanted to pull out some of the key highlights and key things that we found out in the field. So I'm going to start with the multi-head ductless installations. You can see in this picture at site 5, we had a single outdoor unit on the right of the picture with a group of line sets heading off left, enclosed in some casing to bring those to the indoor heads at this site. Some of that extra wire, particularly the brown, there were a couple wires from our instrumentation during the process of the install. So it's not totally wrapped up yet in this picture, but illustration of a system from the outside. Lindsay mentioned this, but one thing to point out at some of these sites is that, especially with electrically heated homes, but it's also true for homes of all heat types, is that the existing systems can be a little more complex than you might first assume. At this site, for example, we had some in-ceiling radiant panels, as shown by the IR image there. You can see the electric resistance radiant heating elements running through the ceiling. We also had some baseboards, and they had a big old wood fireplace here in this site. And so understanding those existing systems and how they're controlled in the space can be really important to the installation. You also have this idea that's particularly important on multi-head systems is where do you put the indoor head? How much load is available based on the airflow and floor plan of the unit, and how are the existing systems zoned, and can you take advantage of that and so you don't leave spaces abandoned. So this site, we see a plot on the left that shows the energy use of these various systems. And the solid lines are the capacities or sort of the fits. So what we expect those zones to need for heat. The red data is kind of the master bedroom, and the green data is kind of the living space on the first floor. And those were sort of the zones that seem to be best fit for an indoor head at each of these sites. They relatively match the 1.5 ton size of the indoor heads and had a large enough zone and square footage that the indoor head would be appropriately sized for that zone. For example, you'd want to avoid something like in the second floor of this unit if you had this master bedroom and the second bedroom on that floor on the same thermostat. If that thermostat was located in the master bedroom and you put a heat pump head in there, that thermostat could be satisfied pretty regularly without any real knowledge of where the temperature in that second bedroom is. And so understanding some of these zoning and sizing implications is important for these heat pump installations.
Hey, Ben, this is Lindsay.
Yeah.
I'm getting some comments that your audio is coming in and out, and it might be because you turn your head based off of where the microphone is. If that's the case, just to consider that. Somebody said they lost their video. I still see my video, so I hope that's just a one-person problem. But just wanted to acknowledge that for folks and make you aware, Ben, in case you're moving your head, and that might be the case. So
okay. I will try to stop moving. If it continues, let me know. I can switch my microphone setup to try something else.
Okay. Sounds good. I've been hearing you well the last slide. I hope that's the case for others. And so we'll interrupt you again if audio comes goes
okay,
out.
Sounds good.
Okay.
Yeah, okay. I will take that note. Thank you for letting me know. So in addition to kind of the install characterization, there is some trade-offs with these 2-to-1 or multiple indoor head systems. So this project is some of the first kind of true cold climate data on some of these different multi-head system installations. And so we are also registering some trade-offs between the benefits of multi-head systems and some complexities to their install design. So on the plus side, these multi-head systems, we have a multi-zone approach that's much cheaper to install than what was used before, which might be something like several outdoor units matched with single indoor heads or 1-to-1 systems. So they're less expensive, and you can displace more heat than you would be able to with a single 1-to-1 system, just because you can have more zones and more areas of heat that you're supplying inside. But there are, like I said, that does come with some trade backs. So we are noticing some controls and performance complexities to these systems. So this plot shows the delivered COP of a single double two-headed system over the range of outdoor air temperatures. Each dot on here, again, is a call for heat with the system. The lighter points on this plot are times where both of the indoor heads ran for the entire heating event. As you get down to the darkest plots on here, those represents time periods where with essentially only one of the heads was on for the whole heating event, or one head was on for half the time and the other head was on for half the time. And so the thing that we're noticing is that the more often you can get both heads running for the full period, the more likely you are to sort of hit the design specifications or the max COPs of these systems. But if you have one head on and one head off, or the head's modulating, you're less likely to get that desired COP. That said, you're still getting a very high COP with these systems. They're still much more efficient than the baseline system you're likely to be operating, but there is some trade-off here in performance. The other thing that we really dove into on the multi-head systems was the controls choices. So this is a site where we're replacing heat from an electric boiler and a baseboard system. And we tried 3 different control modes in the system, denoted by the different colors here on this plot. And this shows kind of the component runtimes or heating system runtimes from the baseboard on the left, boiler in the middle, and the heat pump on the right. In the first mode, we sort of just left it up to the site to set their set points between the boiler, the baseboard, and the heat pump, and let the systems control how they would. In mode number 2, we went in and we tried to prioritize the set points. So this is just using the thermostats to control, but setting the set points lower for the auxiliary heat for the electric resistance systems than on the heat pumps, in order to prioritize heat pump running so that the heat pump would run first. And then in the third mode, we installed a third-party controller that used air temperature sensors and prioritization to try to optimize heat pump runtime, make the heat pump run first before using auxiliary heat. And so the big takeaways from this were, when kind of left up to its own control, we saw quite a bit of baseboard runtime in the red, a decent amount of boiler runtime, and still some pretty good heat pump runtime. But as we increased control to thermostat set points and then to the third-party system, we saw the boiler runtime reduce and essentially be very limited under the third-party controller in mode 3. We also saw the baseboard period tie what we assume is more with occupancy, so it wasn't always on. Some days it was on quite a bit, and other days it was barely on at all in the controlled modes. And we also saw the heat pump usage, especially in the third-party control mode. The runtime on the heat pump was increased. And so as we look at sort of total energy consumption, we saw about a 15% reduction in total energy use at around 20 degrees outside in these systems, when we were totally controlling things, compared to when we allowed the site to sort of just set their set points as they would. So that it still is delivering, having about a similar amount of runtime and keeping the house at a similar temperature. It was just transitioning more and more of the heating use to the heat pump as it was being prioritized over other control modes. So I want to move to some of the ducted system performance. So this was a variable speed heat pump that was installed with an existing air handler, replacing a single stage heat pump that had been there before, an older single stage heat pump. This specific install was installed with like I said, a variable speed heat pump with that was allowed to have its own thermostat, the site's own thermostat installed, which had some controls implications. So this relied exclusively on the thermostat's control algorithm in the site. And we've seen 2 different types of control being used by thermostats. The first we'll start with on the right here is a switchover set point. This is probably the control method that you're most familiar with. It's probably the most common for heat pumps. And this is based exclusively on the outdoor air temperature. So in this plot, what we're seeing is something that's an example where we have a really cold morning. It's below whatever the switchover set point is for the thermostat when the system calls for heat, and the auxiliary heat, shown in green, comes on to meet that at that cold morning. As the outdoor air temperature warms through the day, when the second call for heat came on in this example, it was warm enough outside that it was above the switchover set point, and the heat pump was allowed to run for as long as it needed to meet the load of the house. On the left-hand side of the screen, we have a thermostat that controls the heat pump by staging. So this is a different approach. It's essentially independent from the outdoor air temperature. And in this mode, we have the heat pump is tied to stage 1 heating on the thermostat, and stage 2 is tied to the auxiliary heat. And so anytime there's a call for heat in this control mode, the heat pump comes on. It's allowed to run for a set length of time. In this example, it was about 20 minutes before, if the thermostat, hadn't been satisfied in that set time period, then it would call for the second stage of heating, and both systems would run. And so in this mode of operation, it's sort of independent of outdoor air temperature. The thermostat would just run in this mode. And the result we saw from this is sort of the delivered capacity of the system across all temperature bins. So as we're, sort of on the left-hand side of this chart, this is temperatures that occurred between and -10 degrees outside, all the way up to the right-hand side of the chart, which is between 50 and 60 degrees outside. And the boxes sort of range that show the median and interquartile operating range. So most of the operation happens within that sort of squared box in the system. And so what this shows with the heating load of the house overlaid on top. So what this shows is sort of the heat pump is delivering capacity around or above the need of the house to about 30 degrees outside. And then down below that, the average operating condition is well below what the house needs, but there are periods of time where the heat pump ramps up to be greater than what the house needs. And so that indicates to me is that the heat pump was capable of meeting the load of the house, but because of this staged control, we're seeing quite a bit of runtime of both systems across all temperature ranges of the house. And so this control methodology is sort of limiting the heat pump's ability to deliver heat to the home because of always switching to the second stage of heat after being in operation for about 20 minutes. The last site-specific thing I wanted to call out was at site 27 in our study. This was a variable speed heat pump that was paired with a thermal storage device. You can see that thermal storage system is in the center of this picture. On this site, this was again a forced air heated home, a pretty large 3,000 square foot home in central Minnesota. And so the system that was used here was a forced air based thermal storage system, which are available and are being deployed in the state. We often think of thermal storage as a more hydronic or water-based system, but there are forced air systems as well. And there are some real benefits to those systems, as well as some barriers. So in this system, this specific install, we paired a variable speed heat pump. You can see the coil of that heat pump on the right-hand side of the picture, this diagram, number 2. And it's tied into the central air handling unit fan, number 8 there on the left-hand side, and the ductwork would come out of that fan. And in the middle there is the ceramic high-density bricks that are charged with electric resistance heat in the cheap rate periods, typically overnight. And so some of the real benefits of this system is that it allows that charging of the storage when rates are cheaper overnight, if you have a time of use rate. And the system is pretty simple. There's not, a lot of detail, highly complex parts. It fits in with existing systems very well, doesn't require any sort of distribution modifications. The biggest barriers here are that it is charged with electric resistance. So there is an inherent trade-off between using the storage system to heat your home at the lower efficiency but cheaper rate versus using the variable speed heat pump, which is much more efficient, but just is sort of being used whenever the system calls for heat, which might align with peak loads for the utility, or if there's a time of use rate, peak rate times. I'll also note that forced air has some sort of storage density limitations when compared with other storage mediums like water. So at the site, we worked with the manufacturer quite a bit to modify the controls over the course of testing, and try to find a good balance of this trade-off between the more efficient heat pump heating and the storage-based electric resistance heating. Essentially, anytime the storage was on, it sort of tried to predict the load of the next day and charge up overnight so that it was ready to use that stored capacity during the day. We worked to try to integrate this with when the heat pump was going to be most efficient to heat. This plot just kind of shows one example of the kind of comparison. And so on probably the most extreme, so on the right-hand side is the daily system use versus outdoor air temperature with the heat pump only operating. And so you can see that's kind of the pink there is all the heat pump usage. And we see that the heat pump is delivering all the heat to the home, not really using any electric resistance in that scenario under the time that we operated that system. Then there on the right side is sort of the more aggressive or standard controls that they use in the system. And this really prioritizes storage operation. And you see over, even at moderate temperatures, there's a lot of the green, gold, and red colors, which are the electric resistance storage heating. And so kind of regardless of the day, we're seeing a lot of heat being used to charge the storage system. Again, that's, it's probably at a cheaper rate because it's charging overnight, but it is using quite a bit more energy. And so there's some trade-offs there between sort of energy consumption, efficiency, operating costs, and things like that that make the kind of controls more complex in deciding how to set those systems up. So with that said, that's sort of the end of the summary of the site-specific things. Just want to get through a few kind of conclusion slides, and then we'll hold a couple minutes for questions. In general, I would say all the systems, the overall performance, the COPs were really high when running. This is the mini split systems. We got annual heating COPs out of these systems between 2 and 3. And when optimized, we can see that this system at Site 5 was delivering 16,000 BTU per hour, about 1.5 tons of heating at 0 degrees outside. And so the key, so I think regardless of install, we're getting good COPs or good efficiencies out of the system. And the key to delivering as much energy savings as possible, it really depends on sort of, as we've discussed, those design, sizing, and operation controls considerations. Similarly, for the ducted systems, this plot on the right shows the system COP for individual events versus outdoor air temperature. And events here in gold and red are when it's almost exclusively heat pump. But when we allow that auxiliary heat to come on more, the blue and pink sites, we can see that efficiency is dropping closer and closer to the efficiency of the baseline system at COP of around 1. And so, again, really key to delivering these performance benefits is to optimize that runtime and performance of the heat pump. So I'm going to move through this pretty quickly, but in conclusion, we did sort of loop back to the design guidelines and install guidelines that we presented at the beginning of the project, and really narrowed in on some recommendations for what to be considered when we approach these installs, and some approaches to considering them. I think just a thing to call out is that kind of the flexibility of heat pumps is the key and benefit. One of the key benefits of these systems that really allow them to address needs in all sites, but it is also a complexity in that it requires some care to be handled around the installation, and contractors and installers and designers to consider new things that they might not have considered in the past. And I do just want to call out also TRM recommendations. Typically, we handle energy savings calculations based off equipment ratings, and we design our programs around those efficiency ratings. And I'll just point out that, especially with heat pumps, sort of a tiered approach that might be tied to applications. So things like showing that a system operates at a heat pump system operates at a specific outdoor air temperature is likely more important to delivering on those savings than just having a high HSPF system, for example. The TRM can also consider things like how the system is controlled and sized, tying into those savings recommendations, and that there might be some easy advancements here around advanced diagnostics as heat pump systems themselves and third-party tools are used more and more to sort of demonstrate and document the installation condition at the time of install. So with that, I know we're running a little long here, but maybe we have time for a few questions.
Yeah. Yeah, great presentation, Ben. Thank you so much. And Lindsay, there are questions, so I am going to dive into some of those. And if you're open to it, unless the attendees drop significantly, we could maybe go 1 or 2 minutes after the noon hour, depending on the questions. What do you think, Ben? Are you okay with that?
Yep, that works.
Okay. Okay. I'm going to start with what is the minimum outdoor air temperature for air source heat pumps to actually operate with less emissions than natural gas boiler or furnace? I'm seeing many of these charts show operation only down to 20 degrees Fahrenheit. Is it best to use gas below 20 degrees Fahrenheit?
So that's a great question. So, I mean, I guess I'm an engineer, so all my questions have to be answered by the word "it depends," but it does depend on a few different things. I think in generally the reason you see a lot of operation down to that 20-degree range is probably more cost-based than emissions-based. But both cost and emissions are going to largely depend on the utility and the source. So, how clean the electric source is, and prediction, and over the lifetime of systems installed today, that's going to change quite a bit. So I think as we move forward, essentially all operation or, maybe something down to like 0 is going to be emissions beneficial. The rate piece, I think we'll see change, or cost piece, we'll see. It's harder to predict where costs are going to go because electric costs are ever changing. But yeah, on the rate piece, I think right now, I don't have the numbers right in front of me, but it is actually quite a bit cooler than a cost-based switchover. So I think it's, more typically down to something like 5 degrees outside is emissions positive for the heat pump. But like I said, dependent on where your how clean your electric grid is and how efficient your heat pump is.
All right, next question. Do these heat pumps require a small backup heating system, like natural gas, like a natural gas fueled heating system?
Yeah, so I think in Minnesota, for most installations, the vast majority of installations, you're going to want some kind of backup. How much you have to rely on that can largely depend on the heat pump size, and also the envelope size. So it's not really a focus of this project, but I think one important question that CE and others are trying to understand is the trade-offs between, reducing your load by improving your envelope and heat pump size. So if you have a really good envelope and a low heating load, then you probably wouldn't need a backup. But for most houses, it's realistic to have some kind of backup to cover performance in those really cold periods of time that we're likely to have in Minnesota.
Next question. When trying to optimize the heat pump versus furnace switchover temperature, does it make any sense to use the daily heat pump kilowatt hour used as reported by the heat pump thermostat and compare it to the heating degree day data for the same day?
Yeah.
Is there a better way to do it?
So that is sort of, if you have all the data, one of the best things you can do is try to, more accurately characterize the heating load of your house. So when we do this, we do a utility billing data analysis. You could use, if you have a thermostat that reports energy consumption, that'd be another great thing to use. And so using some of that actual usage data is a great way to characterize the load in your home. CE and others are working to develop tools to try to help automate that process for people. That's a lot more accurate way of determining how much heat your house actually uses than things like, manual J or other sizing estimates. I will point out that you probably do want to have some capacity higher than what your actual usage to do things like recover from setback, or if you have it gets really cold over a short period of time, you might want to be able to deliver a little bit higher capacity than what your house actually needs, just to cover some of that changing variation of field work. But yeah, that would be a good way to size your heat pump. I will also note that the heat pump's capacity changes with outdoor air temperature and by heat pump model. So if you have a 3-ton heat pump but you want it to heat down to 10 degrees, it might not deliver that full 3-ton capacity all the way down to the coldest temperatures. So it's important to kind of, if you think back to that, one of those plots I showed early on that kind of compared the heat pump capacity to the load line of your home, it's important to consider that as well.
Thank you. Do you have a list of the specific brands and models used for each field study location?
Yes, we do have the specific systems listed. That'll be in the report. I can share that with people that are interested.
All right. I am going to ask one more question because it looks like we're starting to drop in attendees, and then proceed to conclude. I'll share questions that were unanswered after the presentation. We can work on trying to answer those and send them out with the slide deck within the next couple of weeks, if that works. Otherwise, I still have one other question, though, do see Ben and Lindsay's contact information on this slide, and do feel free to reach out directly to them if as those are interested and need that. So last question. Have you looked at systems like the ones from Canada that leverage a hot water storage tank to store heat and for use with homes that have both in-floor system and a forced air system? Can the heat storage augment enough to address below 0 temperatures?
Yeah, so we didn't look at those systems in this project, but CE has another card project that we'll be presenting on shortly. Lindsay probably knows the actual date, but on air to water heat pump systems. So that is, heat pumps that use a water medium in a storage tank and try and kind of replace in-floor heat. There are systems that, do in-floor heat and can use hydronic air handlers to do forced air as well. So that presentation will cover some of those systems, the system's performance specifically. Yeah.
Excellent. Yeah. There are a couple of questions about the recording of this presentation and the PowerPoint slides of this presentation. So the plan is for the PowerPoint slides with the script to be shared with all registrants in the next couple of weeks. And then, yes, this webinar was recorded and will be posted on the department's website when we can. So this slide shows the department's website where we deploy conservation applied research and development project results, final reports, webinars, fact sheets, other public deliverables here. And when the final report is also ready for this project, which is anticipated in a couple of months, that will also be posted here. The website is currently under construction, so if you do go here and have trouble finding this, the topic of this presentation, or are unable to access something from a different project, please reach out to me and let me know, and I can help you. So yeah, thanks again to you all for participating in the webinar today. We appreciate your interest in these projects. And to follow up on Ben's comments, other staff from Center for Energy and the Environment will be presenting on air-to-water heat pumps on December 19th. The registration has been sent out for that one, or if you don't know how to register and would like to, please email me and I can get you that registration link to attend that webinar. Also on February 20th, LHB and Slipstream will present on results of a commercial field study of phase change materials for passive thermal regulation. And the registration has not been sent out for that one yet, but that will be coming soon. To stay aware of upcoming CARD webinars and get information about CARD final deliverable announcements, please sign up for our Department of Commerce SIP listserv, and that link to sign up for that listserv will be on the PowerPoint slides that are sent out, or feel free to reach out to me if you can't find that. And in the meantime, if you have any other questions about the Conservation Applied Research and Development Program or CARD, let me know. With that, there'll be a short evaluation that launches after this webinar. If you are able to take a few minutes to answer that, we appreciate that always. Thanks again to everyone for attending and speaking at today's webinar. And that ends our webinar. So take care and goodbye.